Good morning, everyone. I'm Phương Ly Pham. Welcome back to the course Food Waste Management. We will continue the third module with a very interesting lesson, which is about the food waste recovery option. Food waste is a huge problem, so by diverting organic waste from landfill and reintegrating it into productive system, food industry, municipality, and farms can reduce environmental impact, conserve resources, and support the circular economy. There are three main pathways for food waste recovery, including reuse for animal feed, composting, and biogas production. We will start with the first option, which is reuse of food waste for animal feed. This is one of the most efficient and economical recovery strategy. It recovers nutrients that would be otherwise lost in landfill and reduce demand for conventional feed crops like corn and soy. It also supports industry in symbiosis, where byproducts from food industry become input for livestock system in primary production. The waste that is redirected to animal feed must be clean, traceable, and free from contamination like packaging residue, plastic, gas, chemical, and pathogens. In primary production, the waste can be unharvested or damaged crop, fruit and vegetable rejected for aesthetic reasons. In food processing, the byproduct like spent grain, whey, bakery offcut, pasta scrap, and oily cake can be excellent source for feedstock. The waste in retail and wholesale like expired but safe products, surplus bread and pastry, aesthetically imperfect item can also be a source of feedstock. In food service, the waste is pre-consumer kitchen waste like peeled and vegetable trims can be used, while post-consumer place waste is usually excluded due to safety reasons. The processing requirement for reuse of food waste for our animal feeds include mechanical or manual sorting and decontamination, which is the removal of plastic, metal, and glass. The heat treatment or sterilization is required to inactivate pathogen according to feed safety regulation. Dehydration or drying is needed to prevent spoilage, extend shelf life, and improve storability and transport. Size reduction in mixing is important to obtain a uniform, digestible ingredient suitable for feed formulation. And finally, a laboratory analysis for nutritional assessment is performed to formulate balanced diet for specific animal. Now there are also advanced technology like fermentation that can improve the digestibility or insect bioconversion that can increase the nutrients content. Since the food waste doesn't end up in landfill, they can also reduce the methane emission. The reuse of food waste for animal feed can lower pressure on land, water, and fertilizer for conventional feed crops. Economic advantage include lower feed costs for farmers and potential revenue for food business by selling byproduct. The nutrients with this approach are kept in the production cycle instead of being lost as waste in landfill or incinerator. This approach can also support the circular economy by promoting shorter local supply chain and increase system resilience. However, it also has some limitation like strict legislation on animal byproduct processing condition and allow waste stream. Not all waste can be used for animal feed. Food safety risks like pathogen, parasites, and chemical hazards like mycotoxin pesticide residue, cleaning agent, and packaging fragment can also be limitation. Waste usually disposed everywhere, and they are highly perishable. So they need fast and controlled collection and transport. The variability of nutrients composition of waste can also complicate the precise feed formulation. And finally, the public perception. There are still many concerns about waste-fed animals, so this problem requires more transparency, certification, and clearer communication. If the food waste is no longer animal for both animal and human, it can be subjected to composting, which is an established and scalable method for converting food waste into nutrient-rich soil amendment. This is an aerobic process, so it requires oxygen. Here, the microorganisms transform biodegradable material into compost, which is a stable organic matter, returning nutrients and organic carbon to soil and reducing landfill dependence. Composting is driven by bacteria, fungi, and actinomyces that decompose organic matter, producing heat, carbonic gas, water vapor, and humus-like substance. It includes four steps. The first one is mesophilic step, which occur between 20 and 45 degrees. Here happen a rapid breakdown of simple compounds. The next step is thermophilic, which occur at a higher range of temperature. Intense decomposition and sanitation happens because at this temperature most of pathogens are destroyed. Then we have the cooling step, the slower degradation of more resistant material keep occurring. And the final step is maturation. Here is the formation of stable humus. The compost becomes safer and stable for soil application. An effective composting requires some key factors like the balanced carbon and nitrogen ratio. Food waste naturally doesn't have this balance, so usually they require carbon-rich bulking agent like straw and wood chips. The oxygen the presence of oxygen is essential because it is an aerobic process. The moisture should be enough for microbial activity, but not so high that block the airflows. The thermophilic condition of composting must be reached and maintained for sanitization, as I have mentioned. And the particle size should be small enough for decomposition, but not too small that block the airflows. And finally, the pH should stay within a range that supports microbial activity, which is around 6 to 8.5. Considering the composting method, the most simple method is the windrow composting. In this method, the long and narrow pipes are periodically turned to provide aeration. It is low cost, scalable, and simple. But this method needs space, and since it is in open space, it's weather dependent. Also, it requires other management. Invest cell composting is enclosed controlled reactor with a regulated aeration, moisture, and temperature. It is faster and give good process control and suitable for food waste with high moisture, but it requires high investment and operating cost and also technical management. Static aerated pie composting. So the pie aerated by blower through perforated pipe. So it requires little or no turning at all. The aeration can be positive, in which the air is pushed in, or negative, in which the air is pulled out. This method offers better odor control, reduce labor, and require less land use than the windrow method. But it requires higher equipment costs, and once the piles are formed, it is very difficult to correct if there's any problem. Vermicomposting is another method that uses earthworm to digest and convert the pre-stabilized organic matter into high-quality vermicompost. This method can give a compost with higher nutrients content, low energy input, and is ideal for small scale. But the earthworm is more sensitive to temperature, moisture, and contaminants, so usually the waste require a pre-treatment. Composting can offer environmental benefit because it reduces landfill volume and methane emission. It decreases leachate formation and protects water body, and it also improves water retention and reduces soil erosion with the use of compost. The compost can enhance soil structure, porosity, and aeration. It can provide slowly released nutrients and support soil biodiversity. And it can also reduce the dependence on the synthetic fertilizers. The economic advantage include lower waste disposal cost, creating jobs in collection, processing, and distribution. And finally, the potential income comes from the sale of compost. However, it also has challenges and limitations, including odor and pest management, especially with high moisture food waste. There can be physical contamination like plastic, metal, glass, and textile that affect the quality of the compost. The composting requires a land use, especially for windrow system. It also requires operational expertise and continuous monitoring in order to keep the optimal operational condition. The variability in feedstock composition can be a big challenge, and in some reason, compost hasn't attracted many attention yet, so the market for compost is still limited or underdeveloped. Finally, we are going to explore the third option, which is biogas production. In another word, is anaerobic digestion. This process can convert food waste into biogas, which contain mainly methane and carbon dioxide. It can be used as renewable energy, and digestate which is a nutrient-rich residue that can be applied as fertilizer or soil amendment. In contrast to composting, anaerobic digestion occurs without oxygen and is widely used in wastewater treatment plant, farm, and municipal organic waste facility. The process includes four steps. The first step is hydrolysis, which is the breakdown of complex organic matter into soluble compound. Then we have acidogenesis, which is the conversion of this soluble compound into volatile fatty acids, alcohol, hydrogen, and carbon dioxide. Then we have acetogenesis, which is the transformation of this intermediate into acetate, hydrogens, and carbon dioxide. And the final step is methanogenesis. This is a step where methane is generated thanks to the activity of methanogenic archaea, which is a type of microorganism. Anaerobic digestion can operate under this condition, like mesophilic condition, which happen at a lower range between 30 and 38 degree, or thermophilic condition, which happen at a higher range of temperature. So food waste is very suitable for anaerobic digestion because it is highly biodegradable and it has high moisture contents. The food processing residue like peel, palm whey, and even meat or fish waste, but it needs to be allowed by regulation. Household and kitchen waste are good source of feedstock and agricultural byproduct like spoiled produce, crop residue, and co-digestion, which is a mix of manure and food waste. There are two types of anaerobic digestion method. The first kind of method is the waste digestion. It can be applied when the content of total solid is less than 20%. This method is commonly used in wastewater and manure system. Since the input is more like liquid, the pumping and mixing is easier, and the operation is also quite stable. But this method requires large reactor volume, more water use, and the final digest state that we obtain at the end of the process require more dewatering. Then we have dry digestion. This is where the content of total solids is between 20 and 40%. This method is suitable for resource separated municipal food waste. It requires smaller reactor volume, lower water use, and it is also good for mixed solid waste. However, since the input is a solid, it requires more complex material handling. Considering the processing design, the system design can be batch system in which the digester is filled once at the beginning of the process and sealed for the full digestion period. It will be open only when the process is completely finished. The gas production reached a peak, then it declined. In the continuous system, there's regular and continuous input and output that keeps the steady biogas production. It is commonly used in integrated energy system. Then we have two types of digester. In single stage digester, all the phases happen in the same reactor. It is simple, but we have less process control. In multiple stage digester, different thing for different phases are used. So it offers higher stability and methane use, but it's also more complex and expensive. The biogas production can give environmental benefit because it prevents uncontrolled methane emission from landfill food waste. It can replace fossil fuel with biogas, which is renewable energy. It stabilizes organic waste and produce order and reduce odor and pathogen load, and it can support nutrients recycling through the use of digestate. The use of digestate can also reduce the need for synthetic fertilizer. About the energy and economic benefit, the biogas can be used for heat, electricity, combined heat and power, or upgraded to biomethane for grid and transport. The anaerobic digestion also reduce disposal costs and generate income from energy sale of renewable energy incentives. However, like the other approach, we also have limitations and challenges in biogas production. The limitation can be technical constraints like sensitivity of methanogen to pH, temperature, toxic compound, and substrate variability. In this process, there can also be the risk of foaming, clogging, and process instability. Economic and infrastructure barrier can also be limitation because the biogas production require high capital and operating cost. It requires skilled operator and reliable logistics for collecting clean, sort, separated food waste. Finally, there are also regulatory and social issues because the installation of anaerobic digestion facility also requires the permission of local authority. Thank you for watching. I hope you enjoyed this lesson. In the next lesson, we will discuss about the application of resource and waste management in business operation context. See you next time.